Hey everyone, how it goes, and welcome back to Computer Science 146. Today we're going to talk more about stacks. In a previous lecture, we went over that stacks are a last in, first out data structure. This is used to process data in reverse order. One thing that we should keep in mind that stacks are really good for using a technique called backtracking. It's also foundational to how the call stack works inside of memory. Some of the most common stack operations are push, that's adding something to the top of the stack, pop, that removes something from the stack, peek, observe the first element but don't remove it, and also print all the elements of the stack. Now, using this concept, we're going to create a game that uses a stack. Let's first say that we had some kind of game board that looked like this. Now let's say that we randomly introduce a fixed number of obstacles, denoted by the X. Now let's say that the player starts right here, and the object of the game is to get to this goal position that's always down there. Now the player is given the options to move north, south, west, and east. We can only move in these directions if they're valid, so if we're starting right here, the only valid moves are going south and going east. We can't go outside the board. Also, if our player is here, we can only go west and east because north and south contain an obstacle. Along the way, we are keeping track of the path that we have traveled. We are then going to update the options to reflect the path that we have traveled. So for instance, we're going to change go west to go back. We have already traveled to that position, so in fact, we're just backtracking on the path. Now let's assume that we did choose go back. Notice it is now go back, go south, west, and east. That is because previously we were north of this current position. Now once the player reaches the goal position, they win, and we're also going to print out the path that they took in order to reach the goal position. In order to make this game challenging, we're not going to show the board at all, and all we're going to do is give the options of how to move, north, south, west, east, and also if they give up. Now once the player wins or they give up, then we're going to show the board. We're going to show how this game can use a stack in order to keep track of the path. One thing to keep in mind is a stack is a last in, first out data structure. So in fact, we can figure out the path from the last positions and follow it backward all the way to where we started. Now let's see this example in code. Now what we have right here is the project already set up and ready to go, and we've included the stack that we have developed in a previous lecture. Now the first thing I'm going to create is a brand new class, and I'm simply just going to call it Maze Game. Now we're going to start out by initializing a couple of properties, and one thing that we did mention is that there are obstacles inside of this maze. We need to randomly select those, so we need a random number generator. So we're going to import java.util.random. That way we can create a random number generator to place the obstacles. Now we're going to create some properties. The first one's going to be a constant. Public static final int maze size, and we're going to set it equal to 10. This is just going to be a 10 by 10 maze. Now we also said that there were a fixed number of obstacles that we're going to place inside this maze. So we're also going to create that as a constant. Public static final int obstacle amount is equal to, and we'll just say it's a 1/10 of the board size. So maze size by maze size divided by 10. Next thing that we need to create is the board for the maze. And to keep this simple, we're going to use a multidimensional array. We're going to create a private, and the type that we're going to use is simply a character. That way we can simply put an X for the obstacle, an O for the player, and also the pound symbol for the path that we traveled. So as this is going to be a two-dimensional array, we include two square brackets. And we're simply going to call this maze. Now we're going to create some constants that relate to the maze. Like for instance, public static final character empty. So this is going to be an empty part of the maze, and we're only going to use the underscore. Next, public static final character obstacle, and just like in our example, we're going to use an X. Next, public static final character player, and we're going to use the O. Next, public static final character path is equal to the pound symbol. Now following that, in order to make our code nice, we're going to create some more constants that relate to the commands. So for instance, public static final string north is equal to the string go north. Now we're going to do the same for south, west, and east, which we have here. There was also one more command that allowed us to backtrack, so we're also going to create string back, that is go back. Now, as we are keeping track of this path, we're going to use a stack in order to do this last in, first out data structure. So we're going to create a private stack I. So we're going to use this stack interface, that way we could either use a linked list or an array stack as we see fit. However, now we have to consider what type of stack this is going to be. Well, in this maze, we are keeping track of the coordinates in order to move around it. Just like any array, you have indices that index into the values of this maze, and the indices are always integers. In order to keep this simple, we're going to create a stack of integer arrays. We're going to use this integer array to keep track of the x and the y coordinates that are inside of this maze. Now we're going to call this stack locations, as we're keeping track of the locations that we have been to. Now, in addition to that, we're going to keep track of our current location with a private int array current location. Now, in order to make this obvious and to avoid confusion, with these multidimensional arrays, I always consider the first index to be the vertical aspect, and the second index to correspond the horizontal aspect. So right here, I'm just going to put a slight comment that index 0 is the y coordinate and index 1 is the x coordinate. This also corresponds to the locations that we're keeping track of here and also this current location. So its 0 index is y and its 1 index is x. I'll even put this comment here, that way it is very obvious. Now once we've created these properties, we need to go ahead and create our constructor. Public maze game. Now once again, I'm going to separate this functionality into a different method, private void init, to initialize the other properties of this game. The first thing I'm going to initialize is this maze. So this maze is a new character array by the maze size. So this creates a 10 by 10 multidimensional character array. Now we're going to initialize all of the elements inside of this array as being empty at first. The best friend of an array is a for loop. The best friend of a multidimensional array is nested for loops. So for int I is equal to 0, I is less than maze.length I++. Following that, for int j is equal to 0, j is less than maze at I dot length j++. Then we're going to index into maze at I, which is the vertical part, at j, which is the horizontal part, is simply equal to empty. So this assigns all the values inside this two-dimensional array to the value empty. The next thing that we're going to do is add the obstacles inside of this array. And once again, this feels like a separate functionality. So we're going to create a different method. Before we do that, I'm going to go back inside the default constructor and call this.init in order to initialize the properties of this array. Now we are ready to add the obstacles. Private void add obstacles. Now we need to randomly select these obstacles, so I'm going to create a random number generator. Random r is equal to new random, so we construct that so we can use it. Now the next thing that we need to do is add the number of obstacles that are defined up here inside of this array. I'm going to use a counting loop to do that, and the best counting loop is a for loop. For int I is equal to 0. I is less than the obstacle amount I++. Now we need to select an x and y coordinate in order to set this obstacle. The first one is going to be int x, and I'm going to assign that to r.nextInt, and I'm going to use the overloaded version of nextInt by passing in maze size. Now by passing in this value, which is 10, this nextInt is going to select values from 0 to 9, as this value is exclusive. And also, this would make sure that this is a correct index. We're going to do the exact same thing for the y-coordinate. That way we also select a coordinate that is from 0 to 9. Now there's a little bit of a trick here, because the thing is, we need to make sure that the coordinate that we selected doesn't already have an obstacle there. We need to select 10 unique obstacles in order to do this. So the thing is, we need to check this if the maze. Now remember, the first index is the vertical part, so maze at index y. And then the second index is the x part, the horizontal part, x. So if maze at yx is not equal to empty, that means there is already an obstacle there. We can't place an obstacle on top of an obstacle. We need 10 unique locations. Now this is important, but also we mentioned that the player starts at the first index, 0, 0. So if this is not empty, or the x coordinate that was randomly selected was 0, and the y-coordinate that was randomly selected was 0, that's our starting position. We can't put an obstacle where we start. If either of these are true, then we're going to call continue. Now what this does is immediately jump back to this Boolean expression. It doesn't update the value of I, it just goes back up here. So we don't increase I by 1, and everything past this is ignored. Yet, if this wasn't true, then we can safely assign maze at index y at index x is equal to the obstacle. Going back to initialization, now we can call this.addObstacles. So now we have created the board. We had made sure that every element is empty, and then we have added the obstacles to the board. The last things that we need to initialize is placing the player onto the board. So first of all, maze at index 0, that's our starting position. So we're going to go ahead and assign this to player. Now we also have to initialize our current location, which is 0, 0. So we're going to call current location is equal to new int. Now what I could do is put new int 2 and then assign it individually to 0 and 0. However, I'm going to do this in a slightly different way. Since I do know the elements that I have to assign into this, I can actually use the curly braces, put the values inside of there, which now constructs this new integer of size 2 and assigns the values 0, 0 individually to index 0 and index 1. This is just one of many ways that we can do this. Now the last thing that we need to initialize is our stack. That way we can keep track of our path. Locations is equal to new, and we'll just use a linked list stack of type integer array. And there we go. Now we have a number of other methods that we have to worry about. The next one that we're going to do is being able to print the options to the player. In other words, where they can move to. So I'm going to go ahead and create the method public void print move options. In order to make this simple, I'm going to go ahead and create some variables, like for instance, int current y is equal to our current location at index 0. And also int current x is equal to our current location at index 1. Always keep in mind, in this example, we're going to correspond the y part as the first index, index 0, and the x part as index 1. Now we also need to keep track of where we have just come from. And see, the thing is, we're using a stack in order to keep track of that, because it is last in, first out. So I'm also going to create an integer array and call it previous location, and I'm going to call locations.peak. Now this will observe the first element on the stack without removing it. Now we need to be able to print the options north, south, west, and east. We need to first verify if that is a valid move, and we have to do this in two separate ways. So let's start with north first. Now in this example, if we are moving north, what we're doing is subtracting the y by 1. However, we have to make sure that that index that we're about to use is valid, because we don't want to go outside the bounds of the array. In order to help us out, I'm going to create another method. Private boolean is valid, passing in an int index. And all this is going to do is return whether or not this index is greater than or equal to 0, and the index is strictly less than the maze.length. If it's within these bounds, then we know it is valid. Going back to our print options, if is valid, current y minus 1. Remember, in order to move up, we subtract 1 from the index. So this verifies if we're in bounds, but we also have to make sure that there isn't an obstacle to the north of us. So then we have to say, and our maze at our current y minus 1 at our current x is not equal to this obstacle. Now, if both of these are true, we could move north. However, before we can print out moving north, the thing is, we may have come from that position. So we also need to verify if we need to say move north or move back. Here's how we do that. First, if the previous location is not equal to null, when we first start out, we have not added that position to this stack, so in fact, previous location could be null. So if it's not null, and the current y minus 1 is equal to our previous location at index 0, and our current x is equal to previous location at index 1, this means we do have a previous location. The y position that we could move to was at the same y position as our previous location and also at the same x position. So this means that our previous location was going north. And in this case, we need a system.out.println back in order to say go back. Now, if that's not true, then we system.out.println north. So once again, when we are printing the options, we need to print out all of the valid options to the player. First thing, as we are moving north, we are subtracting 1 from our y. So if this is valid, in other words, if this index is in bounds, and also if this index is not an obstacle, then we verify, did we come from this and should we say go back? Or if we haven't come from that position, should we just say go north? Now we're going to do a similar procedure for going south. Now if we are moving south, then we're adding 1 to our current y position. And so if that is valid, so we're not going outside the bounds of this array, and if we can move south so there's not an obstacle there, then what we do is verify, was our previous location south? And if it was, we say go back. And if it wasn't, we just say go south. Now we repeat a very similar way for going west. But in this case, notice, we're not using current y, we're using current x. In order to move west, we subtract 1 from that position. So is this x position valid? And if we were to move in that direction, is there an obstacle there? So if it's valid and it's not an obstacle, then once again, if we had previously been there, then we need to go back. But if we had not, we just say go west. Finally, we do the exact same thing for going east. In order to move east, we have to add 1 to our x position. So is that valid? Is it within the bounds of our array? And also, is there an obstacle there? If we have already come from that previously, then we have to say go back, but if we haven't, we just say go east. This is how we can print out the options to the player. Now with these options printed out, we need to give them the ability to move around the board. This once again feels like a different action, so I'm going to create a different method. So we're going to create public void move with a string input. We expect an input to be passed in, and it's basically going to match go north, go south, go west, go east. Now I'm going to first start out with this, and I'm going to explain why we're going to use this a little bit later on. We're going to take our two-dimensional array maze, and we're going to start out with our current location, our y position, at 0. And also, we're going to pass in current location, our x position, which is at index 1. Now, I'm going to automatically assign this to empty. So this, right now, is where our player is located, and we're going to initially assign this to the character empty. Later on, we're going to be moving the character, but only if that move was valid. Now, in order to make this simple once again, we're going to keep track of our current y is equal to our current location at index 0, and also our current x is equal to our current location at index 1. Now remember, Java thinks of arrays as a class or object type. What I want to make sure to do is not inadvertently re-reference the exact same piece of data. So what I'm going to do is make a copy array. So this copy location is going to be equal to the current location at index 0, our y position, and current location at index 1, our x position. Now, just like before, I already knew the values of the elements that I was going to create with this array, so I was able to set it up in this way. Now, once I have all of that, I can start running this functionality. So first thing I need to see, if the player were to input go north, then we need to verify if we can do this. So first, if input dot equals, and we'll do dot equals ignore case, north. So if they input north, then we need to make sure that we can move north. So if is valid our current y minus 1. Are we able to move north, or will this go out of bounds? But also, our maze at our current y minus 1 at our current x position is not an obstacle. So do we not go out of bounds? Is this not an obstacle? Now, if both of those are true, then what we can do is locations, our stack, dot push, our copy location. So this copy is pushed onto our stack. This is where we currently are before we move, and now we can move north. We can do this very easily by calling our current location at index 0. That's our y coordinate minus minus. So by subtracting 1 from this, we've effectively moved up. Now, if this if statement evaluates to false, then that's an invalid move. We're not going to push this location onto our stack, and we're not going to subtract 1 from it, because either this went out of bounds or there was an obstacle there. Now, maybe the player didn't say move north, maybe the player said move south. So we have to run a similar procedure in order to do this. Let's take a look at it. So as you can see, this is a very similar procedure. If the player inputted go south, and if this is valid, now moving down, moving south, we have to add 1 to this current y. Now, if we do not go out of bounds, if this is valid, and if we move down and there's no obstacle there, then all we do is push that copy location, and in this case, we increase the y position by 1. But if that's not true, invalid move. Now we need to do the same thing for going west. In this case, in order to move west, we have to subtract 1 from our current x. So is that valid? Do we stay in bounds? Also, is there an obstacle there? If it's not, then we push this copy location to it, and then we just subtract 1 from the x coordinate. We have to do something similar for going east. So as we can see right here, if the player were to input go east, if we can move east, so we increase x by 1, and that is still in bounds. But also, there's no obstacle to the east of us, then we push that copy location and increase the x position by 1. Going north, south, west, and east were some of the options, but we also gave the option to go back to the previous position that we just came from. Now this one's going to be handled in a little bit of a different way. First of all, here's what we're going to do. Else if input.equals ignore case, just like we've been doing before, and in this case we're saying that the player decided to go back. Now, first thing that we need to check is if locations. Remember, this is the stack where we're pushing all of our previous locations. If we peek at the first element and it is not equal to null, then we know we can go backwards because our stack is not empty. However, if our stack was empty, then we're at the starting position, and this would be an invalid move. Now, one thing that we can assume, by the way that we have been creating this, that if we can go back, then we already assume that that was a valid position, so we don't need to check that. But what we're going to do is create an int array, and we're going to call this the previous location. We're backtracking, so we're going to assign this to locations.pop. So now we just removed the head from the stack. This was our previous location that we had just come from. And so now what we do is reassign current location at index 0 is equal to the previous location at index 0. And also current location at index 1, the x-coordinate, is equal to previous location at index 1. This allows us to backtrack. It allows us to go back to where we had just come from. Now we just need to finish up this method. So if the player didn't enter north, south, west, east, or back, well, that's just an invalid command, so we say invalid move. Now, if we remember, from the beginning of this method, we assigned where the player was at to empty. Now, at the very end, we are basically moving that player's piece by resetting maze at the current location Y, current location X, to that player piece. That way, what you can think of is basically we picked up the player, we validated if that move was correct, and once we were sure that it was correct, we placed the player down. And also, if it wasn't correct, then we just kept it in the same place. Now we can tell the user what directions they can move in, and we allow them to move in those directions. There's a couple of other methods that we need to create before we're finished. Public boolean get when. Now, as it was established in the example, if we can move the player to the bottom right corner, then we have won the game. So all we need to do is return our current location at index 0, the y-coordinate, is equal to the maze.length minus 1, and if our current location at index 1, our x-coordinate, is equal to maze.length minus 1. That is the lower right coordinate. If both of those are true, then we've won the game. Now, if we've won the game, maybe we want to play again. So public void reset. And this is going to be very simple because all I need to call is this.init. This reinitializes everything and we could start the game over again. Now we only have a couple of more methods left. This is just going to involve printing out the maze itself. So let's go ahead and create this first. Public void print full maze. And all we're going to do is print out each one of the characters in this multidimensional character array that we call maze. So for int I is equal to 0, I is less than maze.length I++. Then inside the body of that loop, for int j is equal to 0, j is less than maze.length j++. Then we're just going to print the elements inside the maze. So system.out.print. We're going to use print in order to keep this on the same line. So we're going to print maze at index I at index j. Now also, outside of that inner for loop, but inside the outer for loop, we're going to call system.out.print line in order to jump down a line. Now this is where you can see that the I corresponds to the Y, the vertical part. The J corresponds to the X, the horizontal part. This prints out all of the horizontal elements, and then once we're done with that, we print out a next line, which jumps down one line and starts printing out the next horizontal elements. Now also, we're going to create one other print method. Here's how we're going to do it. Public void print full maze with path. We've been using that stack to keep track of the path that we have traveled. Here's how we could do this. While locations.peak is not equal to null. So that means that there is something still on our stack. I'm going to go ahead and assign int array temp is equal to locations.pop. So we're going to remove the top part of the stack. Now using that temp, I'm going to assign maze at index, temp at index 0, also temp at index 1 is equal to path. That way, we're popping off all the elements last in, first out order in order to place our path inside the maze. Then once we do that, all we need to do is print the full maze. And well, we've already written that, so let's just call it this.print full maze. This is all of the elements that we need in order to make this game. So now let's create a front end. I'm going to create a new class and call it maze game FE, front end, include our entry point in the main method. We know we need some user input, so we need to import java.util.scanner. That way, I'm just going to create a static version of this. Public static scanner keyboard equals new scanner system.in. I'm also going to create a public static maze game. I'll just call it game is equal to new maze game. That way we can construct it and initialize everything inside of it. I'm going to get rid of this auto-generated comment. There's going to be one other constant that I'm going to create, only because this one has to deal with whether or not the player just gives up. Public static final string give up is equal to, well, give up. And we'll use that later on. Inside of our main method, Boolean play game is equal to true, and while play game, we're going to keep playing the game until the user decides to quit. We're now going to prompt the user system.out.println. Welcome to the maze in the dark. We're not going to show the player the maze until the very end. All they're given is the commands that they can use in order to travel it. Now, once we prompt the user, I'm just going to go ahead and call game.reset to make sure that we always reset the game. Then inside of here, I'm going to create a Boolean game over and assign it to false because currently the game is not over, and while not game over, we're going to keep playing the game. Now every time, we're going to give the user their move options. So game.print move options. How can we move in this maze? In addition to that, we can also prompt them that they could give up. System.out.println give up. Then we take a string input is equal to keyboard.nextLine. That way we can capture the input from the console, and then we check if this input dot equals ignore case. We'll check give up first. If the player decides to give up, then we're going to assign game over to true. The game is over, they gave up. But also, we're going to call game.print full maze. That way they can see what the maze was that they got lost in. Yet, if they don't want to give up, then we just call game.move and we pass in that input. Now, after we do that, we need to verify if game.getWin. Have they won? Did they get to the lower right-hand corner? If they had, system.out.println, you win. And then what we're going to do in this case is game.print full maze, but with the path. That way it could show the path that was traveled to get to the end. We also set game over to true. So now, outside of that inner while loop, but still inside this outer while loop, I'm going to prompt the user system.out.println, enter yes to play again. So then we assign play game is equal to keyboard.nextLine dot equals ignore case yes. And if they don't want to play the game again, well, we tell them goodbye. Here's our front end in order to create the game. Well, after we've written all this, let's try it out. Running the game. Okay, we're Maze in the Dark. We could go south or east currently. I'm going to try going south. Okay, let's see. I can go back, which would be technically north, or, well, let's try going south again. Okay, go south. I'm going to keep going down. Go south, south, go south, go south. Okay, go south. Looks like I'm moving pretty well. Go south. Ooh, okay. So I can't move in any other direction, so I need to go back. Let's try going east now. Okay, go east. Okay, I can go south again. Okay, I think I'm at the bottom of the maze, so I'm going to start going east. Go east, go east, go east, go east. And sure enough, we reached the end of the maze. And notice, we also printed out the path that we traveled. Notice here, this was the part where I wasn't able to go south or east because there was an obstacle right there. So this is the part where I said go back, and so then I resumed back on this path and then traveled in this way. In this lecture, we have utilized the stack data structure in order to keep track of a path. As it is last in, first out, once we reached the goal, we were able to backtrack the path that we traveled all the way back to the beginning. And with all that being said, I'll see you next time.